You see. All right, well, good afternoon and welcome to our SIG HPC Education Chapter webinar. Before I introduce our speaker, just a couple of reminders. First of all, if you haven't done so, please renew and pay your annual dues. It's not very expensive, $10 for professionals and $5 for students. We know that some people tried to do this last week and the website was having problems. And now ACM has assured us that it's fixed, and actually I know that for a fact because one of my colleagues has successfully used it to renew his payment. So let me just also note that we'll have our next webinar November 1st at 1 p.m. Eastern. Daniel Garcia from the University of California, Berkeley will be talking about bringing HPC big ideas to high school students and learners worldwide, and later this week I'll post the links on the chapter website. Last thing is that, and I'll put this up at the end as well, in order to do questions and answers, we have a little chat application, and this is the address of that. What we'll do is post this at the end. We'll hold the questions for the end. You just log in with your name or nickname in parentheses, no passwords, and that'll give us a way to pass questions to the speaker at the end of the broadcast. So without further ado, I'd like to introduce G.T. Roble, who will talk today about bringing computer science to all. So go ahead, please.
All right. Thank you very much. I assume everyone can hear me. I am G.T. Roble. I work at code.org as an curriculum development manager, and I am a former high school teacher myself, and I have a lot of experience with code.org in the classroom. And then about a year and a half ago, I left to help develop curriculum full time. So I have been with code.org for 2 of our major projects that I'm going to be talking about today. But I have experience, broadly speaking, with the organization, and what I'm going to be talking about today is an overview of the many arms of what code.org does, and maybe how that mission, how we are trying to help bring computer science to all students, and what that looks like, and maybe what some of the challenges are. So I am personally very excited about a lot of the tools we've made because I saw how impactful they were in the classroom when I was a teacher. So yeah, without further ado, I'm going to share my screen, and you won't be able to see my face, I'm pretty sure, but you will be able to see my slides. All right, so code.org has a mission that every student in every school should have the opportunity to learn computer science. We are hardly the only organization at this point that has this mission. So, for example, Barack Obama said as recently as earlier this year, in the new economy, computer science isn't an optional skill, it's a basic skill. And this is part of a CS for All initiative from the White House that includes a proposed budget of $4 billion and mirrors similar initiatives across the country to bring computer science to all students. This is a photo of Barack Obama participating in the Hour of Code, which is an event code.org helps throw every year. But in general, there is a lot of interest in bringing computer science to all students. And of course, there are going to be some challenges in the way of that. So for example, this is a statistic that we often talk about. 90% of parents want their child to study computer science. Currently, the numbers vary, but somewhere in the range of 40% of schools teach computer programming. That number has varied. I know that new statistics are coming out this year, but certainly less than half don't have any access to computer science education at all. Another very important aspect of this problem is just a diversity problem. So from 2015, only 22% of students taking the AP Computer Science exam were girls, and only 13% were African American or Latino. Similar statistics persist throughout the pipeline for computer science. So the same diversity problems exist in high school computer science, in university computer science, and then in the software workforce. And so these are problems that we are trying to address as well. It's not just growing participation, but growing the diversity of people who are participating in computer science. Again, this isn't just a Code.org initiative. There are many organizations with the same aspirations. There's also just the issue that right now in many parts of the country, computer science doesn't count for credit at the K-12 level. So this number has increased rapidly in the last several years, and many states are interested. But there are many frictions to bringing computer science to K-12 schools. So schools don't have teachers that are certified. Schools don't have programs that they could use to certify teachers, and there just aren't curricula that they can implement. So maybe they're very eager and well-intentioned, and they just don't know how to get started. So this goal of bringing computer science to all students is a very important one, but there are many frictions currently in the education system, especially at the K-12 level, for bringing this to pass. So I'm going to start by talking about one of the first initiatives that Code.org did or used to help solve one of these problems, and that was the Hour of Code. The Hour of Code, at this point especially, is essentially designed to drive interest in computer science. So they're hour-long activities that introduce computer science concepts. They're primarily programming heavy, though that will be changing in the coming years. And they're designed for new learners and teachers. They're supposed to be fun. Having run a number of these, they generally are a lot of fun because students hadn't thought about computer science before. They hadn't thought about themselves as computer science people. And so getting a chance to especially play with some fun characters or familiar characters. I have some Code.org Hour of Code puzzles shown here. So, for example, there's Minecraft, and Star Wars this year partnered with us, and having some of those familiar characters we believe drives interest. There's Anna and Elsa from, oh, I'm blanking. Well, the famous Disney movie from last year. But in any event, having familiar characters to drive interest in just trying these activities out, seeing if you can just get a little bit, get your feet wet with computer science. So this has been running for 3 years now, and it is a highly popular event. So something on the order of 100 million students have participated. This map is demonstrating just how global this event has become. So we have many people participating across the country. We'll hear feedback about how we're not just inspiring students in the United States, where obviously our focus will be, but across the world, people are getting excited about bringing computer science to their schools, and in particular to their K-12 schools. And again, there are many organizations that also throw their own Hour of Code activities, and we happily drive people there on our own website. This happens in December, so this will be coming up this December during CS Education Week. So just in terms of like how people respond to this, I have some statistics. 98% say it's good or great. 85% of those new to computer science that have increased their interest in teaching computer science. We have some other numbers there, but that last one, the diversity numbers, mattered a lot to us because they're much more representative of the population as a whole. So 49% of participants are female, and 39% are from underrepresented minorities. So this is a very successful event in terms of essentially marketing computer science. We try, or I'll just say, I don't think that computer science can be taught in an hour, but we can use an hour to drive interest in computer science and encourage teachers and students to go further with it. And this is what I'm saying. Computer science, or the Hour of Code, is not curriculum. And so once we have developed an interest in studying computer science, we need to give teachers and districts the tools to actually bring computer science to their schools and to their classrooms. So what we've been doing at Code.org is developing a pathway. And some of these courses are courses that we have developed, and some of these courses are courses that we help support either through professional development or by making improvements to the curriculum. So starting all the way in kindergarten up through 12th grade, there are a collection of courses that we support to help motivated schools and teachers bring computer science to their classrooms. Hold on. Oops, there we go. And in particular, I'm going to talk today about 3 courses. I hope these GIFs are showing. There's a lot of GIFs in this presentation because it makes it easy to show the dynamic parts of what we've built. But CS Fundamentals focuses on K-5. CS Discoveries, which I am deeply involved in building now, is for 6th to 9th graders. And the AP CS Principles course is our curriculum to help prepare students for the AP test for the new CS Principles course that actually is live in its first year right now. So I'm going to actually start talking about CS Fundamentals, then I will talk about CS Principles, and finally I'll talk about Discoveries, since that's the order in which we developed them and kind of the motivations around each of those. So first, CS Fundamentals is a K-5 program that we've developed. If you can see here, it is a very simplistic interface, especially at first. The first levels for children are literally just teaching them how they could drag and drop blocks to make code run. And so here they've got the Angry Birds characters, and they're just trying to get the bird to the pig. You might notice at the bottom there, we're already introducing iteration in terms of the repeat block, but this is a very fun, interactive, and simple interface to teach very simple CS concepts. Of course, things can get more complex, so here we're no longer using north, south, east, and west. We're moving forward and turning left. Many of you may be familiar with logo. This is not too far afield from that. And I'm just showing like a progression of the types of tools that we use. We move on. This is an artist level. This is actually significantly more complex. I'm not going to go over what all the code is here, but you can see there's a for loop. It's saying, for example, with a counter from 5 to 100 by 5, and they're drawing different shapes. And so as I show the sequence of concepts that students will interact with, they're using this drag and drop interface, but as it makes it easier to write the code, they are still thinking about how to structure the logic of drawing different shapes. We also have, this is I think one of our most successful tutorials. It's just an Angry Bird tutorial, and in some ways the interface is very familiar to Scratch, if you may have used that, but students can develop games and define the logic for themselves. So of course they could make it work the way that Angry Birds works, but the tool makes it very easy to explore or make things work the way you would want it to, satisfy your own curiosity. Finally, this is, again, I don't expect you to read all of this, but just demonstrating like the degree of complexity. Certainly by the end of 5th grade, students can write very complex code. You'll notice, however, that it is still in block form. I've kind of skipped over this part of the tools, but everything I've shown you so far was student-facing, and so it is a lot of fun, but we, of course, care about teachers. So we've created, on the back end, lots of ways to manage your classroom or check their progress, and that is a part of what we do that is extremely important, because these tools need to be easy for teachers to use and not just fun for students. But this was the first project that we developed at code.org. It's going through an overhaul right now as more and more schools implement it, giving them more guidance on how to include these across grades and having more grade-specific recommendations for when concepts should be introduced. So this course is already in its redrafting stage. I next want to talk about APCS principles. So like I said, this is actually at the end of our pipeline. I'm not sure how many people here are familiar with computer science principles, but historically there were 2 AP computer science courses, so CSA and CSAB. The AB course was removed several years ago, in part because of low participation. And historically, the A course suffered from low enrollment and the diversity issue that I mentioned earlier in this presentation. And so CS Principles was designed to increase interest and diversity within CS. A framework was created by the College Board in conjunction with college professors and high school teachers for this test, or for this class. And the assessment includes a multiple choice test, but it also includes an independent programming and research project. So the class was designed to demonstrate or to include content from many more fields or many more areas in computer science besides programming. So students are expected to learn how the internet works. Students study the global impacts of computer science, and they're actually submitting code that they write, which on the current AP course, or I should say this year they're both current, but on the A course, students were writing Java code by hand. So they're actually submitting the code of a program that they write for this course. So this course has there's a huge undertaking involved in preparing students for this course, or for this test. So we built lots of resources. This is a quick list here, but we built around 100 lesson plans for an entire year of instruction. There's hundreds of activity guides. We have assessments. We have assessment answer keys. We have videos explaining how to teach lessons. We built a number of tools or widgets, and a widget is essentially it's like a playground that allows students to explore a concept without breaking something. So as opposed to just being programming, it's a scoped tool, and I might have some time to demonstrate some of those at the end. We built an entirely new programming environment called AppLab that I'll show off in a bit. And we built tons of videos that explain concepts, and all of these are just given away for free. For example, I know Khan Academy hosts all of our videos explaining how the internet works. But these are high-quality videos intended to support teachers, not only who don't go through PD, but in general, we are aware that our teachers are not all going to have computer science backgrounds themselves. And so the challenge here is, how do we prepare hundreds of teachers to teach a subject that they may not have background in, with the understanding that this is also an introductory course for most of the students, or for many of the students. So this was a significant undertaking. So we built a lot of things. Like I said, we built lesson plans. These lesson plans are highly detailed. They include not only what you're supposed to do, but a lot of my work. This is essentially what I spend most of my time doing, is developing good lessons. We say what you should do, but also why, and we're trying to talk in a very understandable way to a teacher who may not have the background. So sometimes we're explaining content, sometimes we are motivating a discussion by explaining why we're having it, or giving them tips on what they should be looking for. But we have developed tons of resources and surrounding supports to help teachers deliver lessons. A big part of what we do also is just discovery-based, developing these discovery-based tools, because we actually develop lessons with the hope that teachers may introduce the lesson, but then send kids on their way to discover or understand these concepts for themselves. So I won't have time probably to go through all of these, but we have tools that allow students to explore compression and compress text themselves and see how compressed they can make it. Tools that allow them to draw images on pixels in binary, literally by typing the individual zeros and ones. That tool is extremely popular. It is hard to drag students away from it once you introduce it. So for example, we'd include a teaching tip on that. There's a binary odometer there. An enormous tool that we built is the internet simulator, which shows different layers of the internet. Students can send messages broken into packets back and forth to one another. They have an IP address. There's a functioning DNS system, but it's all very interactive. It's all visual, and it allows students to understand the motivations for the different layers of the internet in a much more interactive way. That's a significant tool within the curriculum that we developed. If you think that one of these things is something you'd like me to talk about later, just remember it now, and I'll be sure to. I'm going to be showing a number of tools. So, but I'll keep moving here. We also, like I said, made a ton of videos. Some of these videos are designed to explain how our programming environments work or how to use the Internet Simulator, but a lot of them are universally valuable or useful for any CS Principles course, or honestly any computer science course. So we'll have a video that explains how packets move through the Internet, and we made those with the intention that other curricula would want to use them or other websites would want to. So perhaps the wording was chosen so it would line up with the CS Principles framework, but in most cases it's supposed to be a resource to the community, and we try to do that whenever we build resources, is think about how can we make these generally useful. This GIF, I hope it's showing up correctly, but it's showing our programming environment. It is a block-based environment, but students can easily switch back and forth between blocks and text. AppLab begins, this is the environment you're looking at. AppLab begins with just a simple turtle interface, again, inspired by logo. This is already showing the creation of a button that when you click it, moves the turtle forward. This lesson would show up right at the transition from when students have learned about breaking down complex drawings with a turtle into functions and start moving towards event-driven programming as they build apps. This is showing a more complex app that you might build, and this is an app that switches back and forth between your favorite singer. And so the student is building a drop-down. They're going to type which text they'd want the drop, like when the text in the drop-down changes, they're going to change the visual of the favorite artist that they would like to see. So they're working in blocks, but they're able to drag it in and it immediately becomes text. If they want to work in blocks, they can. When I program in this environment, I usually have the blocks open, but I do write in text. And most of our curriculum can be completed, or essentially all of it, in block mode, but we do try to encourage students to switch over. Like we said, it's an introductory course, and so we know that students won't necessarily come in with the familiarity of text. And here we can see we're switching between Lady Gaga and Taylor Swift, so we have successfully created a simple app. A lot of the power of this environment, we're about to see it, is that HTML and CSS are not actually the most efficient ways of teaching many of the CS concepts we want students to learn. And so here you can see the design mode feature of AppLab, which allows you to drag in elements into your app without actually having to write the HTML or CSS. We do show students in the console, like this is just writing HTML and CSS, but most of that work is actually done for you through the environment. All right, so I'm going to talk briefly about CS discoveries. That was a very quick overview of CS principles, but we've now seen two ends of the pathway of courses that we've developed. So CS fundamentals, in theory, could go up through 6th grade. CS discoveries is designed to fill a gap between fundamentals and principles. So middle school teachers lacked a high-quality curriculum or curricula that they could use to teach computer science, and so I would talk with a lot of tech teachers who are just scrapping things together, or they are pulling from CS fundamentals or other courses designed for younger children, or they're looking towards high school and pulling down materials, but there were not as many courses designed for students in the middle school grades. A lot of schools are also telling us that they want a course before AP. And so even as CS Principles is an introductory course, and it is, the AP moniker in some cases can scare students off and can scare teachers off, and they think, well, let's implement a different course. So there are other courses out there, but these were two pressures that led us to develop CS Discoveries. And so I'm going to briefly talk about this course since it is in development right now. But this course is designed with flexible implementation in mind. So these are the 6 units of the course. This grid is intended to communicate the relationships across the units. So it is 6 units. It could be taught as a full year course. It could be taught as 2 semester courses. And I am aware that many schools will probably teach 2 units at a time in 6th, 7th, and 8th grade. So from the very beginning, we've had in mind that the implementation of this needs to be flexible, in particular because time in the middle school grades is very hard to come across, and so teaching all of this in a single year is probably not feasible. Even high schools, where I think many high schools will implement this course, I don't believe that all of them will be teaching it as a full year, and so we want to make sure that we're hitting our goals in the first semester and then circling back on many of these concepts in the second semester. The first unit is an introduction to problem solving in general, and then how computers or computational thinking can help us attack new types of problems. The second unit introduces web development as an introduction to the types of syntax or debugging or creation that you can do with programming, but it eventually goes into our third unit, where we use a new tool we've developed called Game Lab that allows students to develop animations and games in a JavaScript environment. That'll close out the first semester. In the second semester, we are first beginning with the design process. This is actually largely based on less on programming and more on the global impacts of programming, where students interview people and in their community or in their school and design a piece of software that could solve a problem for them, especially based off of some of the programming skills that they've developed. But it is not nearly as programming heavy. The fifth unit is introducing a little bit of data analysis and a spreadsheeting tool, as well as the impacts of data on the internet and on our society. And the course closes using a new physical computing device that we've partnered with Adafruit to develop, or they've developed and have partnered with us to keep very cheap. So for $20, you get a single board that is very powerful, and I'll talk about that in a bit. And that unit will be exploring the interface between hardware and software. Like I said, there are several tools that we've developed for this course. So this is a quick view of the HTML CSS editing tool that we're actually currently developing. Students will develop their own portfolio in HTML and CSS, and they'll continue to add projects throughout the year. Game Lab, like I said, is visually very similar to App Lab. You'll notice it's the same block color, it's the same blocks to text ability is introduced here. In this environment, students can create sprites, they can animate them. There's a lot of physics that they get for free, so it's very easy to make things move or bounce, and I'm very excited about getting students programming in this environment. We're just wrapping the creation of those lessons, and they'll be published soon. And finally, App Lab does actually show up in that unit where students are scoping out their own app to solve a problem in their community, but it's used here more as a prototyping tool, especially because the design mode makes it so easy to create the elements in your page. And this is much more about prototyping something and getting feedback from a user. So those are the 3 tools, online tools. We also, like I said, have a physical computing device. So this is the Circuit Playground. If you can discern amongst all the lights and components, there are buttons. There are 10 individually addressable LEDs, RGB LEDs. There are 10 capacitive sensors around the outside. There's an accelerometer. There is a speaker and a noise sensor and a thermometer, and all of this is $20, which is a really important part of bringing this to students. A lot of, historically speaking, robotics might have been a way to do physical computing in the classroom, and those kits are a lot of fun, but they're typically very expensive. And so part of meeting our mission was trying to find a tool that would allow students to do physical computing and see that side of computer science without placing inordinate costs on teachers or districts. This device also is very easy to connect to your computer, so our engineers have made it, I believe at this point, you can plug one of these into a USB port on your computer, and it may, the most difficult is adding something to Chrome. It may even just connect automatically at this point, but I know that we're constantly working to make using physical computing in the classroom cheaper and simpler. So those are 3 curricula that we've developed. Like I said, CS Discoveries is still in development, but just because we have these curricula doesn't mean that they're going to get into classrooms. So there are some challenges. For example, actually getting these resources to diverse students. I've worked in public schools. I've also worked in a private school, and the difference in the challenges that are faced mean that we need to be very cognizant of what is necessary to bring computer science to diverse schools. It is generally, I am speaking broadly here, but it's much easier to bring these types of resources when they're free into well-resourced schools. And so we need to develop partnerships, or we need to develop resources that are going to help all students have access to these tools. Of course, we need to find and prepare teachers, and we need to integrate computer science into existing curricular pathways. There is not a lot of space right now in a K through 12 student schedule. And so if we say this is important, we of course have to help districts think about what specifically are we teaching, or where is it going to fit in. So first thing that we do is everything is free. Everything that you just saw is open source. You can find it on our website. If you want access to answer keys, you have to give us your email at some point in time so that we can verify that you're a teacher and not a student. But everything that we develop is free. We're happy if you use it. We're happy if we point you towards something else that will be useful. I am personally, and I can speak for everyone on the curriculum team, very agnostic towards what you, maybe not agnostic. I do not care if you use code.org's materials. I think they're pretty good and I'm proud of them, but if you don't use them and you want to use something else, we don't care. We want them to be free. We want you to bring computer science to your school. We pay for, or help you pay for, by partnering with professional learning partners or your district, professional development. And like I said, almost everything you've seen here is on code.org/educate. So if there was a tool you wanted to integrate into your college class, like the Internet Simulator, or you thought, oh, AppLab looked like a lot of fun, maybe I want to check that out, there's no paywall, and there are very few frictions to integrating that in your own course. We form district partnerships. So these are commitments by districts to integrate computer science into their curricula. At the end of 2015, we had 100 district partnerships with 20,000 teachers trained, and very good diversity statistics on who the students are who are taking our courses. In exchange for these partnerships, districts get first dibs on participation in our professional development, but again, like we said, all of these things are free. One of the other challenges I mentioned is that we need to prepare a lot of teachers, and a lot of these teachers don't have background in computer science. So another part of my job and the jobs of many people on the curriculum team are running professional development or ongoing support of teachers. This summer I was part of 3 teacher cons, which are week-long in-person professional developments with about 180 teachers attending each. They're divided up eventually into rooms of 30, and teachers are exploring the curriculum, thinking about their pedagogy, and sharing their ideas in preparation for teaching these courses. Eventually, this is followed up with local organizations that run 4 weekend sessions. But day to day, there is online professional development, in particular on content preparation. And then we have a forum that I or other members of the curriculum team or specifically hired moderators support. Generally speaking, if you have a question about an activity guide or you'd like to talk about an assessment, you get feedback from me or from one of our moderators within 12 hours. If you write us during the workday, there's somebody online waiting to help you out. We try to provide a high level of support throughout the school year. But TeacherCon, for example, was an extremely successful event. People rated it quite highly, and we're excited to replicate the model next year as we bring CS Discoveries to classrooms. The last thing that we help support is a K-12 computer science framework that was just released. This is not Code.org's framework, but we did help organize it, and some members of our curriculum team were a part of it. This is an extremely important component in the process of bringing computer science to schools. This framework has broad support from the computer science community and represents the knowledge and practices we believe students should develop at different grade bands. It is still a high-level framework, and so it does not include standards that a teacher might use to develop a lesson plan. It is not at that level of specificity. However, it is at the level that a state could take this framework and develop their own standards. And so now that this has been published and now that it has the support of the community, we will see states use it to develop their own standards as we hopefully move towards 50 for 50 states, including computer science in their curriculum. So that is everything I've prepared. I know that was a mad dash through our efforts to bring computer science to all students. I'll stop screen sharing here. There are many aspects of what we do. So if you remember, we started with the Hour of Code. We went through curriculum, professional development, the development of that framework. But in general, I would characterize us as doing all and everything we can to help bring computer science to all students, and there are a lot of interesting and ongoing challenges involved in that. So I don't know what specific questions or things you'd like me to talk more about, or I'm happy to also demo some tools if that's just what you'd like to see.
So just for the audience, just to remind you that we take questions through this chat application. So I'll leave this up for a minute. I know there's a time delay between the broadcast and see if people want to log in and ask some questions. In the meantime, let me ask a couple things to get started.
Sure.
So, first of all, thank you very much. It's a very nice overview of what you're doing at Code.org.
Sure.
For things like TeacherCon, is this something where the teachers have to find support from their district to get to the place where this is happening, or how is that funded?
There are a variety of models. I will admit I am more on the curricular side than the funding side, but to my knowledge, nobody is paying themselves to go to TeacherCon. So, especially if you're a member of a partner district, we will pay for you to get there. It's very nice usually, so like meals are paid for, you get a stipend to spend while you're there. We support evening activities, but it is not up to the teacher to pay to attend TeacherCon. There have been some instances where we have paid teachers on top of paying for their attendance. So we would pay for their flight, we'd pay for their hotel, and then we would pay them for their time. It depends on the type of partnership we have, but teachers are never, to my knowledge, no one that I talked to at TeacherCon was paying for their own attendance at the event.
That's great. That's
yeah.
Excellent.
It is wonderful. Like I am not personally responsible for all of these things, but I am always excited to hear that we're able to provide that level of support.
I see someone did log into the chat but hasn't posed a question yet, so I'll pose a second one. I think the K-12 framework actually involved, I actually serve on the ACM Education Council, and I believe that was a joint effort of the Education Council, Code.org, and several other organizations. Is that correct?
Yes, there is. Most of what, again, this is not the arm of what I do, or the arm of what we do that I'm most involved in. Most of our involvement was in helping to schedule or coordinate the events. A lot of it was the ACM. I know there were other organizations involved as well. If you go to k12cs.org, you can look more closely at that framework. I know, Stephen, you mentioned that people may be interested to know what are students going to look like when they arrive at college now? What type of preparation are they going to have? What will they know? I would say that at this point, this framework is still aspirational because it hasn't been implemented, but I think that would be the best place to go to understand the knowledge and practices students are going to be bringing into college.
Yeah, I think I mean, if you're successful, this would greatly impact what happens at the university level in terms of teaching computer science, I would guess.
I would imagine so as well. I would say one of the challenges that I didn't post about and that I think is going to be exciting to follow, and a challenge that will be challenging, but it will be, is that things are moving down grade levels. And I see that when I develop curricula. Like I said, I began working on the CS Principles project. A lot of concepts, if you go look at that framework, or just the types of requests that we're getting as we develop curricula, involve moving content or moving types of activities to younger grades. And so it's no longer an assumption that, oh, at 5th grade students will have taken no computer science. We are going to see a greater diversity of students arriving at middle school, arriving at high school, and of course arriving at the university level with a wide or a diverse background in computer science, which makes developing curricula hard. I think at the college level, it poses the challenge that it may be possible to skim, essentially, and take students who do have deep levels of preparation, and so I would encourage universities to not do that.
Actually, there's a related question that was just posted,
yeah.
and I don't know if it's something that you have the answer to, but the question is from Eric, and he asks, is there any interest or efforts to look at expanding this project to non-computer science majors at the college freshman level, specifically looking at training computational science in different science domains, where I assume that we'll eventually use computers to do simulations of scientific phenomena?
Sure. So simulations are explicitly mentioned in the CS Principles framework. It's the CS Principles course is also mirrored off of like a CS0 course that would be a computer science course for non-majors. The specific content of that course, in terms of what a student would do, is actually not as rigidly defined as it might have appeared from what I showed. So, for example, you could develop apps and learn how a core set of programming constructs work. You could just as easily develop physics simulations in a different environment. Most of what students are actually tested on is fairly simple, relatively simple, almost like abstract programming. Everything happens in a College Board defined language that doesn't look exactly like any existent programming language. So it is, if you go look at the framework itself, the language is defined. There are things like loops in there, there's arrays, there's conditional statements, but you could just as easily teach different content and still hit those programming constructs. In terms of like computational thinking for simulations, I know other curricula that prepare students for the CS Principles exam may do more than we do. We decided to build apps because we thought it would be motivating and exciting for students, but there's many other ways you could design a CS Principles course.
Okay, sounds good. Are there any other questions? If you have questions, a reminder to sign into the Ajax chat, which is sighpcEducation.hosting.acm.org/Ajax chat, AJAXCHAT. So far, there are no other questions. Could you demonstrate in your slides when you showed some of the programming environments, since they were in the slides, it was difficult to see some of the syntax.
Sure.
Could you take one of those and just do a quick demo, so people could see it a little bit better?
Absolutely. Let's see here. I'm going to all right.
Yeah, that looks much better.
So this is You let me know. Is that easy to see?
Yeah, that's what.
Relatively? Okay.
Yes,
I'm actually going to create a new project, and I'm going to demonstrate a little bit about what the syntax looks like here. So you start out with a blank environment. On the left side here, you have a toolbox that includes all of the commands that AppLab recognizes. They're organized into categories. This might remind you of Snap or Scratch or any other number of programming environments. So early in the course, a student might write a program that's just one line of code, move forward, and this is part of the Turtle toolbox. So if you run it, Turtle moves forward 25. If you want, you could reset and run it again, and now the Turtle is moving forward a farther distance. At the beginning part of the course, students actually develop eventually very complex visuals. Let's see here. This is going to give me an opportunity to show off to show off some of the teacher supports we provide as well. So inside of the curriculum, the final project, they design a digital scene, and we provide example solutions. So for example, I'm about to show one of the example solutions we provide, and the students are drawing a beach scene. This is all commented here. These are different functions because we instruct students to break down their code into large functions defining their behavior. So for example, it's they're drawing the background and the horizon and the waves and the beach and the clouds and the palm trees, and then below they're actually defining those functions. For those of you unfamiliar with JavaScript, which is the language that all of this is written in, all of this is syntactically correct JavaScript. There are a couple of things we've added that I'll show in a little bit. But in general, anything you've written here could be exported elsewhere. For things that are not, for which that's not the case, that uses our library of functions, we are developing basically the ability to export that library as well. So if there was a different environment you wanted to program, you could just do it there. If you've never programmed in JavaScript and you think that it is evil that you can call a function before you have created it, I agree. But nevertheless, that's how JavaScript works, and it actually is pretty nice because it means at the top of your program there's just a description of what happens, and then below the function descriptions. I'll go back here though. This is that AppLab project I was in. If I go to design mode up here at the top, I can easily drag in elements. So for example, this is a button element that I'm going to bring in. Let's say I want a really big button. And then I want to change the idea of this button to be big button and change its color. Let's say to be more red. That looks good. And maybe change the text to be click me. Let's make it even bigger. There we go. So everything I'm doing here is dynamically changing the HTML and CSS, but none of it requires me to write the code. Like I said before, there are programming requirements for the CS Principles exam. They're hard to meet by learning HTML and CSS. So we wanted to create this tool specifically for that course, and none of them are easily met through HTML and CSS. If I want, I can, in this events area, add a event handler to this button, and that'll bring me back to code mode. So if I get rid of my turtle command, we can see here that it's created what's called an on-event block. This is something that we created, and the syntax is on the event that the big button is clicked. And I, of course, could pick other things. So, for example, the mouse went over that, or the mouse went out of the button, but for now let's just go click. Then this will run this function. This function will be called. If I run it right now, all it's doing is logging to the console. So I could say click me, and we can see down here in a console that it says your big button has been clicked. If I wanted, I can go into design mode, and I'm going to make another screen. Let's see, I'll add an image. Steven, what should I show? Is there like an ACM logo? HPC. It's SIG HPC, yes? All right. So I'm just getting the image's address. I'm going to go back to my image. There it is. And all I'm going to do now that I have a second screen for my app, the first one has the big button on it, the second one has SIG HPC, I'm going to go back into code mode, and I am going to use one of our user interface controls to set the screen. So instead of logging that I click the button, I'm going to switch to the second screen. And now when I start on screen 1 and I click the button, I switch over to my second screen. Something you might be thinking right now is, man, that's a lot of blocks. So a big part of our inspiration for developing this tool is we can scope the toolbox through our lessons themselves. So what you're seeing here is full App Lab with everything it can do. It's actually kind of weird that App Lab would have all of these turtle commands, which are more logo-like, all of these user interface controls that are more like apps. I have probably not. We have some really cool features here that have a remote asynchronous. There's a remote data store that you can use that is permanent. So, for example, let's say you wanted to make an app that stored votes on a proposal for what to do for a field trip or something like that. Then you could create records in a table that would store that permanently. We just launched the new data viewer for that, so very quickly we could call it votes. This ends up creating a table that could get populated by your app. Anytime somebody opens it, they could theoretically interact with this database using those database commands. You can always import or export from CSV, and in our curriculum we actually go into a spreadsheet tool and do some investigations with data, and students learn like, oh man, maybe it'd be great if I limit the types of information students or survey takers can provide, because it's probably not helpful to always have free text. So there are some learning objectives we hit through this tool, just with like how data is collected, how it's represented. So that is a whirlwind tour of App Lab. I'm happy to keep talking about it, but was there any specific questions or things you'd like me to go over?
That was nice to see it more specifically. I think that answered my question.
Sure.
Well, let me just take one more minute and ask for any other final questions to be put into the chat bot. And if we'll just wait 1 minute just to see if there is anything else, because of the broadcast delay. I think it's about 45 seconds or so.
Okay.
Okay, lots of ID and toolkits can do this sort of thing. This question is the point just to tie it in with the curriculum, is the question.
I would say that is a fair statement. I would say most things that we do, this is me speaking personally here, not on behalf of the org, but most things that we've done or that I've thought are a novel idea have been done before. So I'm very excited if I ever come up with a new idea. But one of the benefits of this tool, I think, is something that I haven't shown here, so maybe I can go back to showing it, which is the ability to scope the toolbox and focus students' attention on a small part of a challenge. That is a that is a minor point, but I think it's a significant one from student experience. This is the first time they would use the tool, and we've limited it to a single. Toolbox and only 4 commands. We actually do this throughout the curriculum, so you won't have access to the full toolbox in most instances, because a lot of what you'll find there is not actually relevant to the challenge you need to solve. There's also little things like being able to easily integrate instructions on top of it, but admittedly, easily making apps is not, in my opinion, like the innovation here. And even just the fact that you can scope the toolbox is not innovative, but it does give us the ability to combine all of these things in a way that I think helps new teachers and students use them effectively. So,
yeah, I think it is significant that you've integrated this in a hierarchical way throughout the curriculum, because I think that's the major challenge really at all levels, because if at the university level every professor chooses their own language or approach to simulation, and that takes a lot of classroom time, and I'm not sure it gets all across the concepts that are needed throughout. So I think this kind of integrations should be well received.
Mm-hmm.
Well, I believe that's we're about out of time, and I don't see any other questions. So I'd like to thank you again for your presentation. I will be doing a final edit, taking out the pre broadcast material and reposting on YouTube. So I will send you the link for that when that's ready in a couple of days. So thank you again, GT. I really appreciate it.
Yeah.
And thank those who attended today. And we look forward to seeing you at the next webinar.
All right. Thank you very much.
Okay. Bye now.
See you.